Oh, I'm sorry. So the beginning of chapter 24 now, which has to do with Gauss's law. So the first thing we want to do is, first thing I would like to talk about is the concept of the flux. It's raining outside. Well, or at least it was, yeah. So if it's raining, and I would like to collect some rainwater, if I orient my cup this way, I'll get the max, right? It's raining from outside, so I get rain this way. How about if I orient my cup this way? I will get slightly less. If I orient it this way, exactly horizontal, how much rain will I get into the cup? Nothing. So the area of the cup, you can think of it as a vector. This area here, you can think of it as a vector. So if this vector is pointing upward, the rain is coming in, I will get rain. If the area is at 90 degrees, right? If the area points this way, and the source or the rain is coming this way, how much do I get?
0.
If they're at 90-degree angle with each other, I would get 0 rain, 0 flux through this thing, right? So I get 0 flux coming in. Yeah.
In this case, the rain signifies the electric field.
So suppose it's raining electric field. So I want to collect as much electric field through here. I want to get as much electric field to pass through the cup. Well, I want to orient my cup this way or this way. So the area should be as parallel or anti-parallel to the field as possible. If the area points this way and the field points this way, the field will be going in, right? If the area points up and the field is pointing down, if they're at 180, I would have field going into my cup. Okay? And if the area is this way, it points this way, and the field points this way, it means I have field leaving my cup. Right? If both of them are pointing in the same direction, it means I have the electric field leaving my cup. So that's the idea of the flux. So let's define this electric flux. We will define it in the first case where the electric field is uniform, and the area is either parallel or makes some angle with the electric field. And then we will do it when the electric field is not uniform, and then we will go from there and see how it's related to anything, right? Since we're done actually with that chapter, I'm going to erase here so I will utilize the board. So, electric flux. So we're in 24 now. It has the symbol phi, like this, capital Phi, and electric flux like this. I think the book uses the lowercase e, so I'll use lowercase e. Electric flux. So how much electric field is going into an area or leaving from it will equal to this. The electric field times the area. This is of course electric field, right? And this is the area. This is the area. And then if there is an angle between them, I need the cosine of theta. Okay? So now, if theta is 90 degrees, I get no flux. I get 0 flux. Again, just think of the rain or just think, let's say the electric field is coming from the ceiling to here. If I want to collect electric field, I need the area to point either parallel or anti-parallel to the field, right? Here's the area. I mean, the area is here, but it has a vector. The orientation of that area is this way. If I orient my cup this way, what angle does it make with the field if the field is coming down?
90 degrees.
Makes 90. So how much flux do I get? Zero. And that's what the cosine of 90 does. It ensures that you get zero flux through, if it's 90 degrees. If it's 0 or 180, you get the maximum or minimum. You get plus or minus 1. Yeah. Now, it's not always that happy because the electric field may or may not be uniform. So, what is the flux then in that case? It becomes an integral. Oh, before I continue with this, whenever you see a cosine, it's there is a dot product. If you like, it's the electric field dot area, right? Cosine, the magnitude of a dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So that's the dot product. Now, if the electric field is not constant throughout an area, right? Let's say I have an area, my surface or my cup is somehow oriented like this, and the electric field, let's say, is coming this way and this way and this way, and maybe it's stronger here. So how do I calculate the flux? How much field is entering entering through the surface? Well, I will have to divide the surface into little areas dA, take the dot product of the electric field and that little dA, and then sum them up. Because it's not as simple as just saying E dot dA here, or EA cosine theta, because E is not constant, and the direction between the area and the field is not constant. So if it's not uniform, or non-uniform, the flux becomes this. The integral through my surface of E, not dot A, but dot dA, every little bit of area. Every little bit of area. Okay, that's called the flux. Okay, I hope that's okay. That's the definition. And you see, this definition will boil to this definition if the electric field is uniform. Like if the electric field has a constant value, then the E dot dA will just be E times dA times the cosine of theta. E comes out of the integral. And that will be key when we do Gauss's law. All right, so let us do a few examples. So suppose I have a parallel plate capacitor. Okay, so here's the first example. I have a parallel plate capacitor. And here is the capacitor, let's say. This is the plus side of the capacitor. And here is the minus end of the capacitor. Okay. So this side has a charge Q equals to 5 nanocoulombs, and this side has a Q that has minus 5 nanocoulombs. So they're the same charge, but one is plus, one is minus. Okay, so that's the difference. And by the way, I'm looking at the side view, right? The actual capacitor, there are plates. They are going into the board. They actually look something like that, right? And this will. Does that make sense? They're actual two plates. Remember what the electric field, or in what direction is the electric field between the plates?
To the right.
To the right, yeah, from the plus plate to the minus plate. That was the electric field. And if you recall from Tuesday, the electric field between infinite sheets was eta over epsilon naught, or we were able to write it this way. The electric field between two plates is E, and then the charge divided by epsilon naught divided by the area. And the area is the area of the plates, right? So suppose the plates here, they have, each of them has an area of 100 square centimeters. Centimeters squared. In fact, let me write here area, so we don't get, I'll write the full word, area. Okay? You will see why I wrote that whole word in a moment. So the electric field, Q over epsilon naught over the area, so let's calculate it. Q is 5 nanocoulombs, so 5 times 10 to the minus 9. Epsilon naught is, does anyone remember the value?
8.85 times 10 to the 6, negative 12.
Yep, 10 to the minus 12. And then the area is 100 square centimeters, right? So 100. But square centimeters are not the units we would like. We want square meters. So we multiply by a factor of 10 to the minus 4.
Oh.
Right? Because, yeah, you have to do it twice.
Yeah.
A centimeter is 100th of a meter, but we have centimeters squared, so to the minus 4. Yeah. So, do that. Turns out the electric field will be 5.65 times 10 to the 4th. 5.65 times 10 to the 4th. Newtons per coulomb. Okay. So that's the first one. So now, the point was not to calculate the electric field, but it's to get us to calculate the flux through a surface. Suppose I placed a 1 square centimeter between my plates and oriented at 45 degrees. So here, these are the plates. If you like, let's say that wall is one plate, is the positive plate, and that wall is the negative plate, okay? And the electric field will be going in what direction? That way, so it's across the room. Suppose I have my area here. To get maximum flux through this area, this is the best orientation, right? If I do this, how much flux will go through my area? Zero. I mean, I will need the electric field to come through from the wall, but this way, it just passes across, nothing goes through it. So 0. How about if I orient it at 45 degrees? How much flux do I get? Well, it would be the electric field times the area times the cosine of theta. Electric field times the area times the cosine of theta. Let me ask you, why don't I have to do the integral in this case?
Because the field is constant.
Yeah, the field points from there to here, from left to right, and it just doesn't change its direction. It stays in the same direction, and this is a square, or as you know, pretend it's a square, it's a rectangle, and the square is just straight. I mean, if it were bent like this, then the area would have a different angle, right? Because if it's bent, first of all, if it's straight, the area points in one direction. If it's bent, then let's say this part of the area would point down, this part would point that way, this part would point that way, right? So the area is changing its direction, but it's not. So we just have this. So it would be the simple form, this one, EA cosine theta. And that's what I'm going to write to calculate this. So I'm placing here a little square, a small square that is 1 centimeter by 1 centimeter, 1 centimeter by 1 centimeter. That is one square centimeter, and it's at 45 degrees to the field. Okay. Right, so my square looks like this. So in this case, then the flux will be E times A times the cosine of theta. Can you tell why I avoided using the symbol capital A here?
You have 2 areas.
Yeah, I have 2 areas. I have the area of the plates, and then I have the area of the surface that I have placed between the plates so that the electric field will go through. And it would have been confusing, probably. So that's why I reserved this one for the area of the little square. Yeah?
Should that E be phi?
Oh, yeah. Yeah. Yeah, hey. Doesn't look right. Good. So E is that 5.65 10 to the minus 4, 10 to the positive 4. The area is 1 square centimeter. 1 square centimeter is 10 to the minus 4 meters, right? A 1 square centimeter is 10 to the minus 4 meters, so 10 to the minus 4, and we said the angle is what?
45?
45, yeah, I said 45. 45. So that's calculated. And that will give me a chance to, oh, it turns out to be about 4. So just 4. Now, what are the units? I didn't mention that, but can we tell?
Newtons meters squared over coulombs?
Yeah, the electric field is newtons per coulomb, and the area is meters squared, so, yeah, correct, that's right. Yeah.
If the field on the right had been like -3 nanocoulombs, for the field, would we have to like subtract it?
This is -3, and this one is 5.
Yeah.
And then you have to to determine first what's the field.
You have, yeah.
Once you find the field, you will use that field to calculate.
Right, and so like to calculate that field in the middle,
Oh, yeah.
I would use the like 1 Q minus the other Q, right?
Yes, yeah, right. So
Okay.
you will have, let's say, sigma 8 over epsilon naught
Right.
from this one, and this one will have a different eta over epsilon naught. So yeah, essentially you will be subtracting the fields
Okay.
here.
Got it, thank you.
And I believe we did one where, no, it was a worksheet, where we had one surface had a 2 eta, the other one has a negative eta or something like that. But one of them had something like that. I forget the actual problem. Yeah. Okay, so now comes to the conceptual questions. If you haven't, please grab one of these if you haven't. I printed it out so you can look at it. So let's take a look at the first question. We have, I will try to draw it on the board, but you have a better drawing on your page there. So here is the question. Suppose I have a minus Q here, minus Q. So it's a negative charge. There. Okay. And I have a plus Q here. Positive Q. Minus Q. Okay. And then I place my surface between them. So those are the two charges. And I place my, well, I can use this. So my surface is here. Okay. My surface is here. And so let's draw, how do I draw this? Oh yeah. Like this. Okay, that's my surface. And suppose this is the positive, this is the orientation of the surface. By n hat in the picture there, n hat is the direction of the surface. Okay. Does that make sense? So with the analogy of my cup here, if my surface is this way, what's the orientation of the surface? Suppose I'm using upward to be the z-axis. What's n hat? Positive. Positive z direction, positive k hat. This way, suppose that's the x direction. What's the orientation?
Positive.
Positive I hat. And if that's the positive x direction, suppose this is the positive y, this would be positive j hat. So as my surface has a different orientation. So in this case, they are saying this is the normal of my vertical surface. It points in that direction. Okay. Now, they say, is the flux through this surface positive, negative, or 0? So let's think of, first of all, the electric field due to the positive charge. In what direction will it be?
Left to right.
And I will use red for the electric field due to the positive charge. So the electric field due to the positive charge is away from the plus, right? So it will look like this. Right? Now let me use a different color, blue. for the electric field of the minus charge. In what direction is the electric field due to minus?
Going forward.
Always towards, so it will look like, if this is the minus charge, electric field is always towards it. So what do you notice about the red field and the blue field? In what direction both of them are?
Right.
This way, right? To the right, kind of, in some direction to the right. So they are anti-aligned with the normal, right? The normal is this way, exactly to the left. And these are kind of, they have a right component. They have a component to the right. So E dot dA, when I calculate the flux, I have to do this integral, right? So that means E times dA, E times dA, E times dA, sorry, times the cosine of the angle between them, right? Now, what would the cosine be? Would it be plus or minus?
Minus.
Negative, yeah. If they're anti-aligned, the angle will have a negative cosine. Yeah. Does that make sense? If they're exactly anti-aligned, what's the angle?
180.
180, yeah, and cosine of 180 will be negative 1. In this case, they're not, I mean, in the middle they are at 180, but anywhere else, for example, let's say here, the field will be pointing this way and the normal is this way, so the angle is more than 90, somewhere between 90 and 180. It still has a cosine of negative. So that means the flux is what? Negative. And I think that's the, yeah, so it says plus, minus, or negative. So negative, right? Okay. Let's go to the next one. You have a few cases now. I think you know enough now to actually do this and discuss it. And I want to do just 5 minutes to kind of discuss this one. So for example number 2, maybe I will write it here. Or if we're done with this one, can I erase this one?
Yeah.
Can I? Okay. So and let me sketch example number 2, and then we will go over it. I give you a moment to discuss it with others. So for the second example,
For example,
example 2. So you have several cases, right? For example 2, the normal is in a certain direction and the field is in a certain direction. And I give you the exact angle. Some of them are 180, some are like 30 or something, some are like 60, and some are 0. So you're supposed to determine what the flux is in each case. So I give you a moment to discuss that. Okay. Feel free to talk or walk around if you like also. And I will pause this for a second. Yeah.
And then, no,
And then this is 30. I think this is gonna be like the smallest, largest.
and then,
I feel like this is like we're skipping. Yes, it was like yeah, me too. Yeah. That was never like calculated. Yeah, me too. I was like, oh no. This is gonna be Makes sense.
They're in college. This guy's in college. Yeah.
I like the worst.
The worst.
The most negative, right? Anybody else has a question for me, or I can walk around?
Oh, wait, no.
Just by logic, like since the middle thing,
No, you're right. Wait, actually,
because
yeah,
that's
it's one.
what
Yeah,
That was so like helpful. I appreciate it.
It's nice here.
Oh, thank you.
This guy, yeah. Nah, I'm gonna try it, just not tell you, because.
It was 142.
Bullet? Yeah. Oh. Oh, yeah.
Oh, I see, I see.
Like,
Okay, yeah. All of them. So I use this one to get any.
Is that how you do it?
I don't know. Like, I matched the case on the flux, right? So I was like, this is case one, right? So case one is the worst. But I mean, you can still order this. This was the biggest one.
oh, it's an actual just
Big. But yeah, I have a pretty my personal.
That makes sense. I paid $10 for that. It's like,
Oh, you just got, you paid $10 straight up, you know?
yeah, but I'm really
Yeah.
yeah, I know people do.
Which one, the solar ship?
No, just the
So, let us discuss this. Since in all of the cases, the electric field is going from left to right. So, I mean, we're in the classroom, so it's helpful to just imagine the electric field is coming this way, across the room, right? That way. And let's see how our surfaces look like. In the first case, how is here's my rectangle, right? Here's my rectangle. And here is the normal to that rectangle. How am I going to orient my surface in the first case? That one. That one, yes. It's this one. So the electric field is going that way, right? Let's say the electric field is always coming this way for this problem. And my normal is this way. So what angle do they make with each other?
180.
180. Okay. So case one, we have an electric field of E over 2. So you got an electric field E over 2 going that way. And my area is this way. So I would have the flux, let's call it P1. And it's constant, right? There is no integral in this case. So it would be the electric field times the area times the cosine of the angle between them. The electric field is E over 2. So E over 2. The area is A and then cosine of 180. So flux 1 will equal to minus, this is negative 1, right? Cosine of 180, so minus 1/2 EA, right? 1/2 EA. And let's do case 2. Case 2. Let's think of case 2 now. How does it look like? It says, well, the electric field is still that way, but it has magnitude E, or E0, E. And then my area now is pointing kind of, so here's my area. How should I orient this thing? This way?
Oh, no.
Yeah.
Yeah, this one is here.
This way?
Yeah.
Yeah.
Yeah? I think so. Yeah, it says it's oriented slightly downward, this way. Yeah, this way. If it were this way, what angle does the electric field make with the area if it were just upward this way?
0.
Yeah, that would be 0, right? Because electric field is to the left and my area would point to the left. But in this case, we're tilting it by what?
30 degrees.
By 30. So what angle do they make with each other?
60?
30.
Oh.
It was 0,
Oh, yeah.
and I tilted by 30, so 30. Yeah, so 30. So we have this. In this case, we have the electric field is this way, just E, and then my normal is pointing that way, so they make a 30-degree angle. So we have flux 2 is the electric field, which is just E, right? Earlier it used to be E over 2, but in this case it's E, times the area, times the cosine of 30 degrees. Cosine of 30 is radical 3 over 2, right? Square root of 3 over 2. So phi 2, cosine of 30 is the square root of 3 over 2 EA. In either case, flux 2 is larger than flux 1, right? And why? Well, this one is positive, this one is negative. So whatever it is. So let's do case 3. How many cases do I have? 4. Okay. So case 3. So the electric field is still coming that way. How do I orient my surface for case 3? This way. Yeah. So what's the flux? Okay.
0.
Yeah, the angle is 90. Cosine of 90 is 0. No flux. So in case 3, 0. So here's case 3. The electric field is this way, and then the area is this way. So there is a 90-degree angle. So the flux in 3 is just 0, right? Cosine of 90 is 0. Okay. Now, yeah. Any? How about the other one? The other one is, here's our electric field, it's still going that way, and then my area is pointing in what direction?
Downward.
Downward by how many degrees?
60.
60.
Yeah, it makes a 60-degree angle with the field in this case. So 60. 60. And the electric field strength in this second case is what? In this fourth case?
Stronger.
Yeah. So case 4. Case 4. Here's case 4. You have an electric field. How strong? Is it E over 2 or 2E?
2E.
2E, case 4. Yeah. 2E. And then the normal is this way, right? So 60 degrees. So cosine of 60. So you will get phi 4 is equal to the electric field strength, that's 2E. The area is always A, it's the same rectangle, but cosine of 60. Cosine of 60 is 1/2. So you just get EA. So phi 4 is equal to E times A, right? Do they want from small to large or large to small?
Small floors.
Small to large, okay. Well, the minus is the smallest, so phi 1. And then it's, what's the next smallest?
0.
The 0, yeah, phi 3. And then what's the next smallest? Let's see, phi 2, yeah, because radical 3 is like 1.7 something?
2, so
and over 2, so it's 0.85 or something, right? Yeah, so it's less than 1. Yeah, so P 2. And then 4, right? Yeah. Sounds good to me. All right, so that's the answer to that one. Okay. And one more. Yeah, just one more. So let's go to example number 3. Example number 3, where we have a cylinder now, a closed surface. And the question is, in what direction is the flux? What's the question? Which cylinder or which phase will experience the smallest amount of, or the most negative flux? The most negative flux. So for that one, let me just try to help. If it's okay, I'm going to again erase in here. Can I do that? Can I erase here? Objection? Okay. Okay. So let's erase there. Now, how do you determine the direction of the normal if you have an open surface versus a closed surface? So here's what I mean. This is a rectangle. In what direction is the area? It's kind of ambiguous. Am I talking about this one? This one? Or am I talking about the backside? So if it's an open surface, how do I tell?
By the direction of the electric field?
The direction of the, let's say, well, you still can tell the area.
No.
Yeah.
Yeah.
So you have to be told.
Oh,
And
okay.
that's why you were told in those cases. Right? The previous cases, I told you the direction of the normal. For a closed surface, on the other hand, the direction of the normal always points out of the surface. If it's closed, so go to the back of the surface. So here is a surface. This is a cup, and let's say it's closed. The direction of the normal, if you're here, it has to be out. Direction of the because it's closed, so it's out. If you're here, it's this way. It's always perpendicular to the area. It's closed. It's always out, not into. Always out. If it's a closed surface. So on this end, it would be this one. Okay? It's a closed surface, so there is no ambiguity. It's always out. So let's look at now this, and it's defined to be always out for a reason you will see pretty soon. So here is we have a non-uniform field. For example 3. The field points to the right, but it gets stronger as you go to the right. It becomes stronger and stronger. Okay? So the field points to the right, but it gets stronger, right? So in here, let's say it's this large, and then in here the arrows get longer, so it's a stronger field. So it always points to the right,